Okay, looks like the attendee list is stabilizing, and we'll begin the presentation. So my name is Brady O'Leary. In case you're wondering who you are listening to, I'm that guy. Screen here. Should be able to see me, I think. Maybe, maybe not. It's not showing my webcam. Maybe you can see me, maybe you can't. Either way, if you can't see me, that's okay. It's probably to your benefit anyways. This presentation is the Alpha and Omega Lagoon Aeration Efficiency by Design. And it's a bit of a play on words, Alpha and Omega. It's meant to designate that we are going to talk about kind of the beginning and the end of lagoon aeration efficiency and all the facets of it. And it's also a play on words in that we will be talking about alpha, and ohms at least are relevant to electricity. I'm not going to be talking about the level of detail to ohms, but it's a bit of a fun name. And the picture you're looking at in the background is something we're really excited about. It's something that I think is the future of wastewater lagoon systems. It's not quite here yet, but we'll talk about what we know to date. So I'll get my mug out of here so we can focus on the content and carry on. So before we get into the presentation, I want to talk about the realities of a wastewater lagoon system. And the reality is wastewater lagoons are kind of like this. They're like an old pickup truck, 1970s, really cool, very simple, very straightforward. The towns that have been operating them have been doing so for 40+ years. They're very straightforward. When something's wrong, they know that you go tap on the carburetor, do something else. With that being said, it's older technology and it's not necessarily that efficient. Maybe it doesn't always do what you want it to do, but it's predictable, right? And as town administrators, operators, or engineers are thinking, we want to upgrade this, right? We want to bring this lagoon system into the modern age. Generally, what they come up with is something very expensive, fancy, complicated, and that is not necessarily what lagoon operators want. If a town operator goes to an engineer and says, fix my plant, treat all these new constituents and make it efficient, the engineer is going to show up with something like this. And I don't know how many operators you guys know if you're not an operator yourself. I can say the ones that I know, if I were to show up and offer them this, I can tell you where they would tell me to stick it. It's not necessarily something that they're looking for. They don't want something fancy. They don't want a sea change from what they've always known. So what we want to do is have conversations in this presentation that are not taking it to the fanciest, shiniest, most expensive thing on the planet. It is, what are realistic changes we can make in the lagoon system? What are realistic technologies that we can add to a lagoon system to bring it to the modern age, to make it a bit more efficient? So for an overview, the presentation will go as follows. Before even the triple point intro, I'll give you a bit of a me intro. You might be asking yourself, why am I going to sit here for the next hour and listen to this guy talk about energy efficiency in lagoon systems? My answer to you is, I, by myself, rewired or wired a 220 outlet. I can see it right there, and I didn't die. But more seriously, I didn't do it correctly. I think the outlet is installed upside down, and in general, I think electricity is magic. I don't know why electrons wiggling 400 miles away can charge my phone. But what I can tell you is how lagoons work and how energy efficiency interacts with wastewater lagoon systems. I've been on wastewater lagoon systems. I've been around wastewater lagoon systems, been looked at hundreds, if not thousands of lagoon systems, different designs. Have not been in a lagoon system yet, but I plan on being in the market for a while, so there's still time for that to happen. In general, this has been my entire professional career, and energy efficiency is top of mind with every project that we do. We're then going to have a real brief triple point intro, and then we're going to answer the question, why do we even care about energy efficiency of lagoons? Why is this important? We'll talk about why aeration is the focus of this presentation. Aeration is the primary driver of energy efficiency, the primary thing that you can modulate or change to increase energy efficiency in your plant. We'll talk about design strategies for energy efficiency. So if you're an engineer, this is probably, in your designing plants for the future, this is a great section for you. Or if you're an operator, you can talk to your engineer about, I want this or this thing designed into my system. We're also going to talk about operating strategies. So if you are that operator, what can you do to increase the energy efficiency of your plant today or with minor modification? And lastly, we'll talk about that teaser photo I had at the beginning, the floating solar on a wastewater lagoon system. It's called photovoltaics. And it's a play on photovoltaic. And we'll talk about, is this the future and what are considerations for that? Also, I've broken this down into 9 strategies that you can use. This will span the design and operational strategies, but these are takeaways that you can take back and hopefully improve your system or improve the design of a system that you will be implementing in the future. For a brief triple point intro, as you guys know, if you've been around the triple point ecosystem, we have this phrase, lagoons do it better, kind of similar to that truck photo at the beginning. We're trying to fight this conventional wisdom that as people are expected to upgrade their lagoon systems, they have to go to some fancy, expensive, complicated process. We're here to say, in general, the lagoon is the best system for your small community, and we have bolt-on or drop-in processes that can help that lagoon system treat as good or better than the activated sludge plant while using the infrastructure you already have. In general, we have a tailored process. Every lagoon system is custom, and then therefore the system we put into that lagoon system is a custom product. And everything we put out there, we stand behind. We have a we say we do a guarantee. If we say it's going to work a certain way, it better work that way. Otherwise, we got to get in there and figure out why and make that better. We get involved pretty much after head works and before disinfection. Most of what we do is aeration upgrades, ammonia removal, nitrogen removal, phosphorus removal, and so on. And everything's made in the USA. This is really important these days with the Build America, Buy America Act. Everything's made in the United States, and we are headquartered out of Colorado, in Centennial, Colorado, right outside of Denver. This is where all of our aeration products are made as well. Okay, let's get to the real important stuff. Why do we care about energy efficiency in wastewater lagoons? And you've seen this graph before in different presentations. And the point generally is there's a lot of lagoons, and if you'll notice, they're centered heavily around the Midwest and then down into the South a little bit. And if you compare this map to the next map, this map is a map of the least and most energy efficient states, with light being the least energy efficient. And if you look, California, obviously California is #1, deep blue, very energy efficient. But the area of light blue coincides pretty directly with the map of lagoon systems in America. Basically, the states that have lots of small towns haven't had energy efficiency initiatives like grants or incentives to have these municipalities go and inexpensively upgrade their system. What this means is that most lagoon systems are operating on the old inefficient technology that they were designed with in the 70s, 80s, or 90s, and there's a very untapped opportunity to get in there and upgrade those. We can make big impacts with minor changes at these lagoon systems. And we do that by focusing on aeration. Aeration is absolutely the primary driver of the energy expenditure at any wastewater facility. Over here in the top right, your average activated sludge plant will spend maybe 54% of their capital on aeration energy. But if you get to lagoon systems, it's closer to 78 or 80%. So if we're going to go and try and make that lagoon system more efficient, making a UV system more efficient is not really going to move the needle. Making the aeration system more efficient is definitely going to move the needle. And fun fact, if you look over here, there is there's not a town, there's a country of South Africa where they did a study of the different lagoon technology or the different treatment technologies and to determine how much energy expenditure per cubic meter of wastewater treated across different technologies. What they discovered is that lagoons are actually the most efficient technology from a wastewater treatment standpoint. If you have the space and you have the time, you can treat the water very inexpensively. So the average, if you look at, for example, emissions emitted by a lagoon system treating its wastewater, you compare it to activated sludge, it is more than 4 times more energy inefficient to do activated sludge than it is to do a lagoon system. So that's a pretty fun fact. But we're working in a cool industry with a cool market. Since aeration is the primary focus, we have to go back and do a little bit of aeration recap. I know you've probably watched multiple other aeration webinars that we have. The intent of this is not to get into the details, but I think recapping it's pretty important. for building the rest of the presentation. So I will blast through this section here just to kind of give you a refresher. So what is aeration? Aeration, obviously, as you probably know, is not just adding oxygen to water, but adding oxygen to water and mixing to the water such that the bacteria, the waste, and the oxygen are constantly in contact. We can't forget about the mixing component of adding oxygen to water. Why do we need oxygen in wastewater? It's because the bacteria that are already there, the bacteria that wants to eat the waste, and we want them to eat the waste, they respirate like we do, and we have to give them dissolved oxygen so they can complete that respiration and complete that digestion. So to treat a pound of BOD, it's 1.5 pounds of oxygen is required for respiration. To treat a pound of ammonia, it's 4.6 pounds of oxygen. And the oxygen that we're putting in, generally, in 99% of the cases, is just free ambient air oxygen. The air that we breathe right now is 20 to 22% oxygen. So we're just going to pull that out of the air and get it into the lagoon somehow. And why do we need mixing? We need mixing because that is not a peanut butter cookie. That is not a cake. That is just a bunch of ingredients that are not well incorporated. No different than if we were to put a bubble in one end of the lagoon and waste in the other end of the lagoon, we're not going to get the treatment that we expect. What you have to do is mix it up so all these things are in contact with one another, and when we're able to do that, a certain reaction is allowed to take place. In this case, it might be a cake. In our case, obviously, what we're looking for is bacteria digestion. And how do we aerate? We aerate with getting some level of interface of the air, just the ambient air that we were talking about, and the water, such that the ambient air oxygen can transfer into the water. There are some things that help that transfer. Pressure, for example, if the pressure differential or the pressure of the air is higher, it's easier to push dissolved oxygen into the water. If there's turbulence, churning of water, like maybe you would see in waves or a waterfall, that kind of entrains oxygen in the water, giving more air-water interface, allowing more oxygen transfer. Circulation also helps, pulling low dissolved oxygen water from the bottom of the pond and bringing it up to the top and exposing it to the oxygen is helpful for transfer. And there are multiple kinds of aeration. There's natural aeration, wind, waves, that sort of thing, waterfalls, mechanical agitation, surface aerators, there's air diffusion, and then there's oxygen injection. So just kind of a refresher here on what these might be. Mechanical looks like this. The idea is we're going to move the water, we're going to throw it around to create surface area, create that air-water interface such that the oxygen can be transferred. And it's done in various ways. Surface splashers, aspirators, turbo units. This is it looks like a house brush aerator. There's air diffusion. The idea is we're putting air in at the bottom and letting it bubble up to the top, creating oxygen transfer. And there's fine bubble aeration, creating a lot of surface area versus coarse bubble aeration, very little at least comparatively, very little surface area. But the idea is release from the bottom, bubbles to the top, kind of a fizzy action. And lastly, there's this new concept of air injection or oxygen injection into micro bubbles. I put this as a question mark. Is this actually aeration? This is oxygenation, but because the bubbles are so small, they come out like this and they kind of float in the water column. They don't really rise rapidly. They don't create a mixing action. Are they really completing the EPA definition of aeration? I say I don't believe so. This is more of a supplemental oxygen addition, but this is not something we see used very commonly because of the lack of mixing. So why do we care about aeration equipment? Why am I talking about all these different technologies? The reason is that they all have different levels of oxygen transfer efficiency. So if you look at the fine bubble membranes I talked about, we'll say they're 4 to 7. What Triple Point uses is also 4 to 7. Coarse bubble tubes, the less efficient version of the fused aeration, might only be 2 to 3. And surface aerators are 1.5 to 2.25. And to clarify, this is standard aeration efficiency. How many pounds of oxygen per horsepower per hour are we imparting into the wastewater? And this is a pretty important number because it's not just how efficient are we at transferring oxygen, which is OTE, it's how efficient are we transferring oxygen in relation to the energy required to do that. We're bringing horsepower into the equation. And this is why standard aeration efficiency is a better measure of efficiency. But if you look at this chart, you'll see that some of these are pretty low. compared to the higher efficiency options. So, coarse double tubes are about half or less than half the SAE efficiency of fine bubble membranes. So we have an opportunity here. Same with surface aerators. So we'll talk about that in a little bit from an efficiency strategy standpoint. And what it comes down to, why there's a big difference between that fine bubble number all the way at the top and that surface aeration number all the way at the bottom, is the primary reason these two different technologies work. Surface aerators take the water and fling it around, or they move it, or they propel it to entrain or trap or put into contact oxygen with the water. They're moving water to get in contact. Diffused aeration, on the other hand, moves air to get it into the water. And it does that through varying different technologies of efficiency. And what it comes down to is moving air is simply less energy intensive than moving water. And when we're moving air, we can release a big bubble like you see here. We can release medium bubbles, or we can release multiple bubbles. So we take this bubble, it has about 5 square feet of surface area, air contact with the water. We have this bubble, or 4 bubbles instead, would have 180, the same air, would have 185 square feet of contact. And I don't have the math on how many this is, but we'll say 600 bubbles has 1,800 square feet. I did do the math, though, on 1 SCFM, standard cubic foot of air per minute. So we're pumping 1 standard cubic foot of air per minute into the water. It broke it down to 2 millimeter bubbles. That would be about 6.8 million 2 millimeter bubbles put into the water every minute. It's a huge amount of air. And that's 914 square feet of surface area per minute. If we were to run this up to the surface air, the airflow that most lagoons are running at, let's say 1,000 SCFM, that's almost 1 million square feet per minute of surface area contact we're putting into the water to allow that oxygen transfer. And this is why fine bubble aeration is simply more energy efficient. And we're putting 20 acres of surface area out there every minute at 1,000 SCFM. It's a pretty big deal. I don't want to argue this point. This is not really the point of this presentation. I would say most people in the industry generally accept the truth that diffused aeration is the most efficient and effective lagoon technology out there. In a lot of ways, treatment technology, it's used by all the big plants on the planet. We're talking about a 400,000 gallon a day lagoon system. This truth is generally accepted up to the trillion gallon plant in Chicago. They use the same technology. One important factor, a bit of a public service announcement or a warning, is to trust but verify. When someone tells you how energy efficient they are, it's important to have them back that up with a third party. Especially in lagoon systems, you have engineers working on these plants that, a small town engineer might do a lagoon system every 5 years or 10 years. They might not be up on the newest technology, the newest procedures, and it's very easy for people to be duped by somebody selling snake oil and saying they have the best things than sliced bread. I promise you, if they're telling you that their technology is better than everybody else's, and they can't really show you why, and they can't prove it externally, that's probably a bit of a red flag. So what we recommend is having somebody do a third-party independent evaluation on the technology. This guy is somebody we hired, Dave Redman. He's one of the greatest experts in the industry. He's got no agenda. He doesn't want you to like triple point versus any of our competitors. He's just going to give you the cold hard fact. So if you're looking at aeration technologies, make sure they have independent ASCE studies. And with that being said, this study can actually be gamed in itself. I did a whole webinar on this a year or two ago about the nuances of the ASC study. So if you want to nerd out on oxygen transfer, go watch that study at lagoonuniversity.com. And when you have this information, from the third-party study, what you can do is go and look at how this device works in these varying conditions. In our case, how much coarse bubble to fine bubble ratio do we have? How deep is it? What is the airflow? And then with that data, we can interpolate what the efficiency is instead of just making it up and being wishful. We want to have good data and to make good decisions with that data. So the very obvious efficiency strategy, number one, that derives from this discussion that we've just had is replacing old inefficient equipment. And I don't want to talk about this too much because it's very straightforward. So let's just do a couple of quick examples. Here's a plant in Texas, it's 0.26 mgd, and let's say by design they require 4,700 pounds per day of oxygen. With diffused aeration, the Aeries is what Triple Point uses, our mixing and aerating device. It will require 108 brake horsepower to transfer that 4,700 pounds a day into that pond. If they have existing, or they did have existing surface aerators, they had 225 horsepower out there. So just having more energy efficient technology allows you to use less than half of the brake horsepower. And surface aerators also have some downsides of you can't turn them down, they're either on or they're off. And if you do turn them off, you're now having a portion of the pond that no longer has mixing, no longer has aeration, it can create dead zones. So if we're replacing 225 horsepower of surface aerators with 108 brake horsepower of diffused aeration, we can save 106 brake horsepower. And for this facility, at a pretty reasonable number of 0.8 cents per kilowatt hour, that saves $55,000 per year. More than $500,000 in 10 years. That's a really big deal, and that's before any operational strategies that could be employed to make that system even more efficient than it already is. And we'll talk about those later. But that's upgrading the surface aerator plant. Here's another plant. Let's see if this plays. Another type of upgrade that you can do if you have a coarse bubble system. This is Chile Lake, California. It's a 0.18 mgd plant. They required 320 pounds per day of oxygen, and they had a coarse bubble system that was already in existence. When we did a design with our older aerator, the Mars diffused aeration system, let's see if we can move this forward. Yeah, you want visuals. The Mars diffused aeration required only 8.5 horsepower, and the coarse bubble system they had out there was already operating at 22.5 brake horsepower. So just by changing out the aeration end, the business end of their system, we were able to save 14 brake horsepower and over $9,000 per year. In general, if you're going from a surface aeration plant to a diffused aeration plant, it'll be around 50% more efficient. If you're going from a coarse bubble plant to a fine bubble plant, it'll be about 1/3 or 33% energy savings. So this could have a pretty big swing depending on different site conditions, but that's a good rule of thumb. One of the cool things though, when you're upgrading a coarse bubble system, you don't have to replace the entire system. They've already got blowers, and I can guarantee you they provide enough air unless the design conditions have changed. And they already have a header infrastructure. So really all you gotta do is get out there and change, again, the end of the system, the diffuser end of the system. It's a very simple upgrade. Okay, so those are the easy energy efficiency strategies. And before we get to the more complicated ones, we need to talk about some fundamentals of aeration efficiency. In 1 second, I just want to check some of these questions here. Okay, I'll come back to the presentation. So the fundamentals here, and this isn't necessarily really interesting stuff unless some of you might find it interesting. I do, but it is important to understand as a background to the energy efficiency strategies we're going to discuss. Okay, so the first one is alpha, and as you remember the presentations, the alpha and the omega. Alpha is a really big deal, and it's kind of a hidden factor of efficiency. And what it is it's a corrective factor. We do all of our ASCE testing in clean water because clean water in one state is very similar to clean water in another state. And then we correct, the alpha factor corrects for that value for use in dirty water. So if we did our test of our aerator in clean water and I put it out into a really intense wastewater, we need to correct for how much less oxygen transfer we're going to get based on what might be in that water. It could just be a high MLSS, it could be fats, oils, and greases, it could be detergents, but it is a corrective factor used in every aeration design. And it's really important to understand what it is and not to underestimate it. I can't tell you how many manufacturers I've seen come in to a pulp and paper plant, with really nasty, really difficult water and treat it like, it's tap water, because it's not. It's much harder to transfer oxygen into intense, high fog wastewaters, and you need to account for that up front. And this factor, the alpha factor, has the heaviest impact of any aeration calculation on oxygen transfer. It's more important than elevation and pressure and that sort of thing. It's the biggest lever to pull to decrease oxygen transfer. So it's important to be aware of what the alpha factor is in your plant, or what are the contributors that detract from oxygen transfer in your plant. Do you have lots of fats, oil, and greases, or detergents? Do you have an industrial plant somewhere in your process that's sending some nasty stuff that's actually inhibiting treatment in your facility? Because we can be as efficient as we want to be. You can spend money till you're blue in the face on the most efficient technology to transfer all the oxygen in the world to the water. If the oxygen can't be transferred to that water because of these surfactants or whatever, then you're just off-gassing air to the atmosphere efficiently. So we have to create the air efficiently, but make sure it's being transferred efficiently. If you have an industrial plant on your collection system and you suspect and you can prove that they are increasing the alpha, or decreasing rather, the alpha factor of your plant, you can have conversations with them about pre-treating. Perhaps they can put a DAF in to strip off some of the fats, oils, and greases, that sort of thing. But definitely be aware of this factor. A very important factor also is depth on oxygen transfer, especially when we're talking about diffused aeration. Because diffused aeration is 100% about, that's a bit hyperbolic, it's not 100% about bubble rise time, but bubble rise time is very, very important. What it comes down to is, as that bubble rises in the water column, it has more time to transfer its resident oxygen to the water around it. So if you have a 10-foot deep lagoon, it's going to transfer, it's not linear, but approximately half the air that you're going to put in a 20-foot deep lagoon with the same amount of air, because the bubble simply is rising through the water column for double the amount of time. So the deeper, the better. And it's expressed in percent per foot. So a good efficiency for a reasonable normal efficiency for a diffused aeration system is 2% per foot. And if we're at 12 feet, we can expect to transfer about 22% of the oxygen in that bubble to the surrounding water. This is a really important factor for plants that have variable depth lagoons. If they're raising and lowering the lagoon depth, then they're changing the oxygen transfer constantly. I'll show you the impact of that a little bit later. Another fundamental to understand is flux rate. You know, people talk about surface aerator efficiency, and it's like, if it's on, it's one efficiency. If it's off, it's not efficient at all. Diffuse aeration is not that way. It's more of a continuum. It is, and there's two interrelated factors. So we've got pressure and energy efficiency. They're related. So what you see here is a typical graph of energy efficiency. On the blue line, we have oxygen transfer, and what it's showing is the more air we put through this diffuser, the lower the oxygen transfer is. And that just means we're trying to shove more air through a fixed space, and we get less efficiency the more we do that. You still get more oxygen transfer the more air you push through it, but the relative efficiency decreases as you do that. But it's a bit of a double whammy, because as you try to push more air through that device and you're losing efficiency all along the way, you're also increasing the restriction, the airflow restriction, or the back pressure. So we have head loss over here as you do it. So we're decreasing efficiency, and the back pressure increases the pressure, which you'll learn next increased costs. And you get kind of a double whammy effect. So pushing too much air through a diffuser is not necessarily a good thing. You want to be careful about how much air you're putting out there. And it becomes a trade-off between capital costs and operating costs. Some people might want to install the cheapest aeration system they can, or least expensive, as they might say. And we'll say, we'll put 25 aerators out there, and we'll run them really inefficiently, and we'll pay a lot of money to do it. The capital cost might be, you know, a couple $100 grand, but they might pay 30 grand a year in energy costs instead of 8 grand a year in energy costs. And we look at the lifespan of a typical wastewater treatment facility, 20 years, that payoff actually happens pretty quick. So just know, the more air you put through a diffuser, the less efficient from an energy standpoint it gets, and from an oxygen transfer standpoint. Another fundamental to understand is system pressure. System pressure is the #1 contributor in an aeration design to how much horsepower that plant requires. So it's the primary contributor to the brake horsepower demand. And it's most impacted by depth. That's the #1 reason pressure goes up. So for every foot of depth you increase a plant, it increases the required pressure by about 0.43 psi. So to pump air 10 feet deep, you're going to need at least 4.3 psi just to get the air to the bottom of the pond. So if you look at a typical plant, well, again, made up 1,000 SCFM and made up elevation, this might be in, I don't know, Illinois, 1,000 feet of elevation. If that plant was run at 6 psi, it requires 40 horsepower. If it's run at 11 psi, it requires almost 70 horsepower. So you can see there's a pretty linear correlation of the deeper I go or the more pressure I need for whatever reason, the more horsepower is going to be required to get air to where I need it. And you can read horsepower as cost. So for every horsepower, it's 0.746 kilowatt, approximately on average, that you're paying for that energy to create that level of pressure. So brake horsepower equals cost. And there are other contributing factors other than depth as well. You've got header design, how big it is, how long it is, how many restrictions we have along the way, and anything else that might be creating restriction like a fouling aeration system. We'll show you the impact of this later as well. And there's a few other DO basics that we should discuss. Dissolved oxygen is dependent on the saturation point of oxygen. So it's easier to transfer oxygen in the middle of winter, where the saturation point might be 14, than it is to transfer oxygen in the dead of summer, where the saturation point might be 9. Total dissolved solids also affect dissolved oxygen transfer, and pressure definitely affects oxygen transfer. Again, the more pressure there is in the air, the easier the air can transfer oxygen to the water. The DO delta, like where we are now and where I want to get, is also pretty important. So basically what it comes down to is water with no DO is much easier to transfer oxygen to than water with 10 DO. So it's easier to transfer oxygen at lower dissolved oxygen. If we're trying to run a higher buffer oxygen transfer content or dissolved oxygen content, it's going to require more energy to do that. Okay, so let's get to the meat and potatoes of the presentation. It is your lagoon system, and how do we design this, if we're designing it to be brand new, to be as energy efficient as possible? And as we jump into that, let's talk about another lagoon reality. I'm going to ask you a question. You can't obviously answer me, right? But answer it for yourself in your head. What do engineers not like to be? And that answer is they don't like to be wrong. They're not in the business of doing things wrong. They're in the business of getting things right. And because of that, they over-design plants on purpose because they want to be good stewards of their town or their customer. They have to make sure they account for every possibility for that plant. I swear, if on the right we have a picture of, I don't know what car that is, but it looks the same. That's the same gauge cluster that my parents had on their like 1997 Astro van. And if you were to ask a wastewater engineer to design that Astro van to work in any condition, they're like, well, someday they might be on the Autobahn. I can tell you an Astro van has no business going 140 miles an hour. And this over-designed nature is there because they have to account for 20 years of, again, possibilities or eventualities. So they make worst case assumptions. They're going to assume, the town's going to grow to X, Y, and Z. We're going to assume a worst case flow, and we're going to assume a worst case loading, worst case water and air temperature, worst case flux rate, plus we need extra air on top of that because we need a residual dissolved oxygen content in the lagoon. And what that means for you today is that the day you turn your plant on, you are way over capacity. You're putting way more aeration into that pond than is required compared to the design. And there's a potential to waste a huge amount of power in this case. Another important thing that when you're looking at a new technology that we recommend to engineers is run your O&M audits based on reality and not a guessed future condition. A engineer might take a look and say, well, these are the worst case conditions for 20 years from now, and then do an operation and maintenance evaluation on how much that plant's going to cost, and then say it's going to cost that much money every single year. And that's absolutely not the case. We can put in tools to run the system less with a lower airflow rate, with a lower throughput rate, such that the operation and maintenance on day one can be significantly lower than what it is in 20 years. So the first thing is, let's design efficiently. And what we want to do is we want to look at that 20-year condition, but what we also want to do is look at what's it going to be realistically for the next 5 years or so. What's an average we're going to have in the near term? And let me give you an example of how drastic this can be. And the input values are not necessarily irrelevant here. This is just a design that we did for a plant. And you can see it's 0.43 MGD, 753 milligrams a liter. And depending on some different conditions, whether it's depth or time of year, or whether or not we're treating for ammonia, the air requirements are vastly different. So if I'm an engineer, I'm going to come in, I'm going to pick the worst case scenario, the highest one, 7,400 SCFM. But if you look actually at their real world condition, it's 5,500 SCFM. If you look at their real world average condition, they actually only need 2,075 SCFM. So what this goes to show is that based on different variables being changed, the amount of air the pond needs is drastically different, less than half of that design condition. And when we're doing this average condition, it's important to be realistic about what do we think the flows and loadings and temps are going to be over the next few years, next 5, 10 years. Another question is, where do I design it efficiently? So we talked about earlier, the more air we put through a diffuser, the less efficient it gets, but it still works. And what I would do, especially with industrial customers that don't know they're going to have some future condition that's really high, because they want to insulate themselves from it, is let's design that future condition to be inefficient, because we're unlikely to get there, but if we get there, we want to make sure it works. But we're not likely to be operating there for a long period of time. And what that means is, if we're inefficient at this design condition and you turn the airflow down, the cost of producing the air goes down and the efficiency of those diffusers go up. You can actually run the system very efficiently today. And then if you happen to get to that design point, maybe it's a 20-year design point and you get there in 14 years, you can add more aeration, you can modify it then to make it more energy efficient. Pay for it when you need it, don't pay for it all now. Also, as you're designing wastewater treatment systems, it's important to give the operator some levers of control. So getting them a handheld DO meter, getting them VFDs, considering staging the blowers such that, we at design condition, we use 2 blowers, but on average conditions, we only have to turn 1 on. And then providing some mechanism for depth control if the lagoon process allows for it is helpful as well. So if you look at the screen over here on the right, the diffused aeration system, you can ask yourself, where's the restriction? And we say this because restriction increases pressure. As we push air from the blower system up here down this pipe, the longer it goes down this pipe, there are friction losses the whole way down. The first 95 feet has 0.06 pressure loss. This section right here is 0.01, etc. The longer we go down a pipe, the more friction losses there are, and the more pressure is required to pump it down it. Similarly, how big or how thick the pipe is, what the diameter of the pipe is, impacts this as well. If I'm trying to push 1,000 SCFM through a 10-inch pipe, that is going to be a lot more friction losses, you can read that as pressure losses, than pushing it through a 12-inch pipe. And we generally do these calculations as we do installation systems. You can see we calculate every single segment, and getting the air down this entire length is 0.17 PSI. If we were to change that pipe from we'll say an average of 10-inch down to an average of 8-inch, that number would go up dramatically. Another contributor is valves and any other restricting device that you have. These could be control valves or shut-off valves. Those can restrict air as well. And then also the air line itself from the header out to the aerator does have a pressure loss. It's actually a pretty big one. If you look at the first aerators, the first aerator might have a pressure loss of 0.19, but if we get all the way out to this one with the pressure losses of that entire airline all the way out to here of 0.84. And the important thing with diffused aeration systems is you have to design them for the highest pressure loss diffuser out there. If you have one diffuser that's 3 feet lower than all the other ones, you have to run them all at the same pressure to make sure we're getting air to all of our devices. So When you're designing a system, you want a header that has the lowest pressure loss as possible and as few restriction points as possible. And for every PSI, at least of this plant, of this specific one we're looking at, every PSI that we designed out of this design will save that plant $11,700 per year. That's a really big deal to keep this as low pressure as possible. Here's another example. We were trying to get air from where the blowers are here all the way across this, what looks like a 500 or 600 foot wide lagoon, and that was creating way too much back pressure, at least 1.2 psi to get the air all the way over here. And it's silly for them to pay for that every year, day in and day out for the next 20 years. We looked at a different design scenario where we wrapped around the header right here and brought the air to this side and brought the air out from there. And doing that allowed us to save 16 horsepower, brake horsepower on this design, about $10,500 every year. And I'm just gonna make it up on the whim here. Maybe this pipe over here costs 20, 30, 40 grand. In 4 years, the energy efficiency savings pays for that, and it's cream thereafter. So designing in the air distribution system with as few restrictions as possible, with as least pressure loss as possible, is gonna help save your customer a heck of a lot of money moving forward. The third efficiency strategy is choosing the right blower, and this is not unlike choosing a car for efficiency. Trucks are designed to do a thing, the Prius is designed to do a thing, and they're different things. And all blowers are the same way, they're not the same. So we'll talk about the most common ones here: turbo, centrifugal, screw, PD. And also know you do have a selection in motor choice. You can increase the energy efficiency of at least PD blowers by 5–10% by opting for a more energy efficient motor. So if you're incented, that's another area to look into as well. So what are the technologies? We have positive displacement over here on the left, your two rotating lobes that essentially push the air cavities from one direction to the other and create pressure. A screw system is very similar to the lobe, except for it's twisted over time. And they create a progressive cavity that gets smaller and smaller, allowing it to create more pressure as that air is pushed down that cavity. You can see it right here in this blue column. And then we have a turbo or multi-stage centrifugal. And the idea is to have a very fast spinning device that creates a centrifugal energy that pushes the air. This is actually not unlike a turbo on a motorcycle or a supercharger on a car that you might have. So the positive displacement blower is kind of the standard blower in 80% of plants that you see. And I'm talking about it because the standard blower happens to be the least efficient one out there. There are less efficient options, and I mean, we use these all the time. I don't want to call this not efficient, but it's just kind of the standard blower. And the reason it's not as efficient is that they're prone to slippage. So in the cycle of the rotating lobe, as you can see, there's a space here where high pressure air from one side can slip back. You spent the energy to push the air all the way around and create a high pressure zone, but it can slip back, and this creates losses. As I mentioned earlier, you can add efficient motors, but still there's a lot of efficiency losses because of that slippage. So the energy efficiency is low. They're super reliable. This is why they're used in wastewater lagoon systems. They're pretty bulletproof if maintained well. And they can be turned down quite a bit too, which is a factor we'll discuss here in a minute. You can have it run at full design, or you can turn it down with a VFD to operate maybe at 40% of its overall capacity and still work very well at that point. They work fine with pressure. If lagoon pressure goes up or down, they don't care that much. And because they are the standard blower, they're kind of the lowest cost. This is why they're used the most frequently. Screw is one I really like, especially for certain kinds of lagoons. And the idea is it's the same process of the lobe. We're twisting two lobes together, but we're minimizing slippage by creating a progressive cavity where the air is kind of squeezed all along the continuum as it goes down to create more pressure. Because of this, we don't have as much slippage in a screw blower, and this can save up to 30% in operating costs just because we're not having air squeezing out the back end. But they are also not really a new technology. It's just a twisted lobe. So it's as robust and bulletproof as the rotary lobe system, and as flexible as well. They have great turn down. But because it's a newer, more advanced technology, it is more expensive. So if you're going to use a screw blower, you want it to be in a lagoon system that's deep or has a lot of pressure. They thrive usually above 9 psi. If it's above 9 psi, these are pretty much going to pay for themselves. They're also great for variable depth lagoons. They handle changes in pressure very, very well. And they also handle changes in flow very well as well. So you have a pretty good turn down on these systems as well. And lastly, we have turbo. This is a very specialized kind of technology, but in the right application, it's even more efficient than positive displacement, more efficient than these screws I just talked about. The thing is, turbos are very effective at their design point. If you say, I want 2000 SCFM all the time at the same pressure, turbo is going to be your best bet. So it's best for high, consistent flows. And they can also be implemented in stages. So if you say, I need between 2 and 5,000 SCFM, you can have multiple 2000 SCFM blowers that you turn on and you run consistently to get close to what your needs are. But they're not good for variable depths. If you have a lagoon that's going from 6 to 15 feet, these don't like it. They go into surge and essentially air spills back out, and they simply just don't work. They also aren't very good for large swings in airflow. If you need the plant to work at 2000 SCFM, like the last example, up to 5000 SCFM, this is not the right technology for it. It's not efficient across that continuum. And it's also not very efficient for low flows. If you're looking for a 200 SCFM plant for a really small lagoon in Oklahoma, this is not the right technology. It's very much for high flow applications. So as I mentioned earlier, the turbos are very efficient at their design point. So here's an example. Got a screw blower and a turbo blower. The screw blower has a very flat curve, only about a 5% differential if you're operating from what looks like 2500 to 9500 SCFM. Very flat curve. They don't lose efficiency no matter where it's running. It's also got a very long curve, right? It has a very broad range of operation. A screw blower, on the other hand, it can be more efficient. You see it right here. It's got a 5% efficiency increase only in this band right here. But the line is not as broad. So basically the turbo blower doesn't have as much range. And it's actually less efficient on the low end of the range and less efficient on the high end of the range. So this is why I was mentioning, if you have a very consistent flow, turbos might be a fit for you. Here's a really quick example I did for, I think it was a sugar beet customer. He wanted to look at, he was a big fan of Aeration and Kaiser, and we are too. So we looked at some of their blower offerings, and you'll see it's pretty drastic how the different models approach the need of the plant. With this model, 2 units required, the other models are 3 units required. The brake horsepower swing, depending on the technology chosen here, is pretty drastic, 371 up to 457. So let's say it's about an 80, 90, even more brake horsepower difference, and the cost of the systems are very different. The costs are not important here. This is a huge plant, tons of air, not representative of most lagoons, but the comparison is representative. So I think it's important, if you're doing this, you want to run a sample comparison at any one of your plants to know what the impact is. And one of the big takeaways for me on this was the purchase price doesn't really matter. The biggest impact on energy efficiency is the year-to-year cost, is what it comes down to. So in this plant, it just so happens that the turbo happens to be least expensive on day 1 and least expensive on year 10. This is actually a pretty rare case. This is a case where it was very high flow, consistent water levels, a base load blower. But the difference is drastic. If we were to choose the PDs, for example, there is a $700,000 delta over 10 years, so $1.4 million over 20 years, just on the technology that we chose. And for a difference of what, 30, 40 grand on day 1, very important to understand what is the cost, what is the efficiency of that blower, and what is the impact on the overall cost to run your plant long term. I'm not going to talk much about VFDs, variable frequency drives. You guys probably know the drill, but it allows you to adjust the 60 hertz that comes through the wire to the device to turn it down to, we'll say, 30 hertz, so we can take a blower and cut the airflow in half. This is a tool that operators have We'll talk about those operational strategies here in a second. And on cue, operating strategies for energy efficiency. So these are some toolkit items that an operator has to change the energy efficiency of their lagoon system. First is modulating airflow. That's a really big one. Depth control is a big one. DO monitoring and control. How do we accomplish this? And I have an opinion on that I'll share with you. Making sure we're maximizing the treatment volume of the lagoon, and recirculation, actually, and also proper maintenance. One important thing is to not forget mixing. As we're turning down airflow to your plants, we want to make sure air is still put out there for some level of mixing. If you're a complete mixed plant like this one is, mixing is very important, but even in a partial mixed plant right here, you can see there's kind of a faded area around each diffuser, and that's solids that are being mixed up. So don't turn your airflow down to 1 SCFM a diffuser, because you might affect the operation of your plant. It's important to watch your effluent values as you turn airflow down to make sure that you don't cross a threshold. But if we're turning down airflow 20, 30, 50%, that's not necessarily going to be an issue. Just don't want to forget about mixing. So the energy efficiency strategy number 4, airflow modulation. As we mentioned, when you start up a plant, usually, especially municipally on day 1, we're going to be over capacity, and we want to right size the airflow for what the plant needs. So I'm just going to use Eagle, Iowa, actually it might be Eagle, Idaho, I believe is what it's supposed to be, for an example. So on day 1, Eagle's design might be for 2.8 MGD, 309 milligrams a liter, 20-degree water temperature, residual DO of 2. When in reality, the operator is only seeing 1.9 MGD, BOD of 240, a water temp, a peak of 17, and residual DO of 1. Each one of these deltas, the delta between 2.8 and 1.9 is 56 brake horsepower. That's 30 grand. The delta between the BOD that they're seeing is a difference of 52 brake horsepower. It's 27 grand. That means we can turn the blower down 56 horsepower for this this line, 51 horsepower for this line, and so on. So the delta is 202 brake horsepower for design to 114 brake horsepower today, for savings of 88 brake horsepower. So by turning down the airflow to meet the needs of the actual conditions that we're seeing today, Eagle can save $46,000 every year. So it's important that if you have a new system, you don't get out there, you don't flick it on to full bore, because that's not it's not necessarily the most energy efficient way to go about it. Another strategy, if you're an operator, if you have the ability to adjust depth, is to know how depth impacts your system. Use an example of a customer I was working with in Tennessee. They had 508 SCFM in a lagoon system, and its max was 10 feet deep, but he was running it at 5. And his logic was, I don't really have a reason to run it at 10. I'm getting, it's working just fine at 5 feet deep. Why do I need to go to 10? The difference is you're already paying to produce that 508 SCFM. You're putting it out there anyways. You're cutting in half the amount of time it's hanging out in the water. So at 5 foot of depth, he's only transferring 491 pounds of oxygen. If you were to raise it to the max depth of that plant, he'd be transferring, with the same 508 SCFM, 1,100 pounds of oxygen. Another fun fact is that as you increase depth, you're increasing volume, which increases the hydraulic retention time of the cell. So you're not only getting more oxygen, you're able to get more treatment done in the same space, simply because the lagoon's hanging onto the water longer. At 5 feet of depth, that lagoon's only treating 42 milligrams a liter of BOD. Increased to the maximum depth, you could remove 155 milligrams a liter of BOD. And if you didn't have that BOD to remove, you could turn down the airflow. So if you've got the ability to modulate depth and you don't need the extra freeboard for some reason or another, make it as deep as possible for a diffused aeration system, because you're going to get a lot more treatment in your pond, you're going to get a lot more oxygen transferred. Next strategy is DO control. This is, we want to measure what is the dissolved oxygen in the pond, because what is the demand right now? It's an indicator or a diagnostic tool of, am I putting too much air in or too little? If you see I've got less than a milligram a liter of DO out there, that's a sign you probably don't have enough air unless you've really fine-tuned it. If you see you've got 3-4 milligrams a liter of DO, unless you're chasing a certain kind of nitrification, you might think I have the ability to turn down the air in this case. And it's important also if you're taking DO to not just go over to the edge of the lagoon, flop it in, and take one measurement. It's important to take multiple measurements around the lagoon at multiple depths and also at different times of the day to get some representative idea of what the dissolved oxygen is in that pond. And it's one of the tools the operator can do is play with residual DO values. He doesn't need 4 milligrams a liter, so try 3. And if 3 milligrams a liter is working really well, try 2 and continue to turn down the airflow. And provided you're seeing positive results, that's an easy way to save tons of money on your operating costs. Check it seasonally because the conditions do change seasonally at a minimum. And at the end of the day, DO control with a handheld device is up to the operator's alchemy. You know, it's a way that he can fine tune and tweak, he or she can fine tune or tweak the energy efficiency of that pond over time. And here's a bit of a hot take from me. Everyone thinks, oh, it's energy efficiency. Let's do automated DO control. I don't like it. I think it's fantastic in theory. I think it's poor in practice. First of all, this is a lagoon system. It's a battleship. It's not. It's a tiny little aeration cell, an activated sludge plant. Changing the DO doesn't happen over the course of 5 minutes. It happens over the course of 5 hours or a day. So you can't really fine tune an entire lagoon. And the other issue is there's no one spot out here that's representative of the entire lagoon system. You might have high DO right here and low DO right here, and a DO sensor right here might turn down the airflow too low in a way that affects the system down the way. This is why we recommend a handheld device. It gives the operator the ability to go out there and figure out where the problem is and diagnose it themselves. And lastly, do you trust automated DO control? If you've got 1, 2, 3 DO probes 400 feet out in the middle of the lagoon, and you've got to maintain them regularly, it just doesn't happen in lagoon systems. Regular maintenance is not a common thing, at least maintenance to the level that a DO probe requires. So what happens is operators tend to fall a little bit behind, and they start to not trust the numbers that they're getting because the DO probes aren't calibrated to reality anymore. So in a lot of ways, I see a lot of operators pay a lot of money up front for a device they end up not using. So I'm a proponent of the handheld device. I know we're running out of time here, so I'm going to go a little bit quicker. I recommend an energy efficiency strategy of making sure you're utilizing all the pond volume. This is a lagoon right here where we did a dye test, and we found out the influent was right here and the effluent was right here. So the majority of the pond was not being fully utilized. And here's some computational fluid dynamics we did on another plant. We wanted to find out where the water was going, and you can see here that the water was coming in and actually short-circuiting directly through here. So this yellow area, an underused area of the pond. This dark orange area, especially this dark orange area, very underused area of the pond because the water's coming in and it's swirling around the outside of the pond. So if I'm putting aeration in these underused areas, I'm not actually utilizing the full potential of the pond because the waste is simply not going there. So having a thoroughly mixed lagoon system, making sure that the air and the waste are always in contact is very important. So mixing is absolutely key, and we want to make sure to put the air where the actual treatment is taking place. Here's another fun one. You can get free oxygen by adding recirculation. So what happens is the waste comes through a plant, BOD is treated, ammonia starts to get treated, and then we get most of our ammonia treatment later in the process. That nitrification creates this, which is a nitrate molecule, and that's typically where the nitrification process stops. High nitrate water over here. If we're going to take some of that high nitrate water and bring it into this pond, and we have some anaerobic areas of the pond, which almost always exist in a partial mixed lagoon, what happens is the heterotrophic bacteria can actually rip off these 3 oxygen molecules on the outside of the nitrate molecule and use it for oxygen. So it's a very, very simple way to bring some extra oxygen to the back end of the plant. And the other benefit is this water is pretty much treated at this point. So when we bring it, it generally has high dissolved oxygen just from the wind that's blowing against it. So we're kind of bringing high DO water with an extra reservoir of DO or DO potential in the nitrate molecule. So let's look how this pans out. Let's say we have a standard lagoon, 200,000 gallons per day. The BOD is reduced to 30, the ammonia is reduced to 10, and we've got 4 milligrams a liter hanging out in that final cell. If we recycle that water back, we can get a nitrate credit of up to 95 pounds, a DO credit from just the residual DO and that water we're bringing back of about 7 pounds, with a net difference of about 25% from what the lagoon was designed for and what we're actually going to need with that recirculation. It's important to note that this is not an exact science. Will we get 100% of these credits? Will we get 50%? I don't know. But recirculation is very, very inexpensive, and it's something that an operator can trial. And there's not a net effect on treatment. Recirculation in lagoon systems is, in almost every case, a net positive. It's very inexpensive. And then lastly, the last strategy is maintenance. Maintaining your equipment. As I said earlier, restriction creates pressure, pressure creates more brake horsepower requirement, and that raises the energy requirement. By getting out there and knocking off what might be on your diffusers, you can save thousands of dollars. It can be done very easily from shore, from an air bump procedure, just by modulating valves. You can get a decrease of 0.25 psi. Changing the air filter on a blower will change the inlet pressure, which changes the overall pressure of the system of 0.25 to 0.5 psi. And getting out there and replacing membranes can change the pressure by up to 1 psi. If you remember earlier, at least in that one example, the previous example showed a plant with a 1 psi delta changed the operating cost by about 11,700. Just by changing membranes, we'll say the cost of changing membranes was 11,700. That upgrade would pay for itself in the first year and then save energy thereafter. So I just want to introduce this. This is, I think, going to be part of the future of wastewater lagoon treatment, of photovoltaics. The cool thing about lagoon systems is they've got tons of real estate. It might not be field, but the water surface is real estate where we can float solar panels out on the surface. Lagoons are also great in that they have consistent power consumption. So we have a demand immediately close by where these power panels are. And when designing a plant, engineers and administrators are looking at the long term. They want to pay off, they want the cheapest system for 20 years. They don't want the cheapest system today. Lagoon systems can benefit from this because if the power were to go out in the middle of the day, you've got redundancy such that you can run your aeration system. And there are incentives, depending on the different utility in parts of the country or different states, you can get grants or funding for this kind of initiative. Our understanding is that solar generally pays for itself in about 10 years, which is well before the lifespan of a 20-year project. And another cool factor is it's a de facto cover. It can block out light from the water, and we know from 5+ days of light deprivation, algae will die and it will not grow back. So it's kind of an extra benefit. So considerations that we're learning about this is that it's very dependent on the different utilities. Some utilities will not allow municipalities or independent contractors to do this. The other question is there enough local consumption? The power that's generated needs to be used nearby based on how most of these utilities operate. So if Lagoon system only has a 10 horsepower blower, putting a couple solar panels out there is probably not going to be a good idea. You need a kind of a critical mass, a larger plant for this to make sense. Utility also has to have net metering required. What this means is that we overproduce energy in the day, and the utility gives credits for that overproduction at night, because obviously the system is not going to be producing energy in the middle of the night. So you get the credits for the overproduction during the day, such that the net utilization of the plant is zero. And another question is if I need a 4 megawatt system with this much surface area, do I have enough room to put that system out there? With most lagoon systems that we're looking at with this, the answer is yes, but it's a worthwhile consideration. This is very much at the early stages of this technology. I don't have any evidence for this, but my gut tells me that we're about 5 years before mainstream potential. But this is where we see it going, and this is where Triple Point wants to take it, because we always want to do something better, do something cooler for ourselves, because it's fun to do cool stuff, and do something that benefits our customers for the long run. So kind of getting back to the car analogy here, we don't really want to keep working with the 1970s truck because it might not work efficiently, but we don't want to give the operator something they don't want to use. So let's be realistic about the upgrades that we do from the efficiency standpoint. Maybe we give them a Ford EcoBoost, maybe we get real fancy, we give them a Ford Lightning. We have to give them the technology and operational parameters that are reasonable for Lagoon systems. But in general, the equipment the lagoons have can be upgraded for high efficiency, and they can be designed more efficiently on the front end, it can be operated more efficiently by the operator, yielding huge results, very impactful results from a dollar standpoint. A normal reminder we've got, this webinar is a part of a series that we do. We have a whole bunch of webinars on demand. In the past, we've been able to give CEUs for this, but in general, there is a wealth of knowledge that you can learn all kinds of new things, from algae to oxygen transfer to removing sludge while a lagoon system is not drained. So I highly suggest, if you want more content like this, check out lagoonuniversity.com and learn some more. And as you know, we've got a Lagoons Do It Better community. We do informational blogs, we do educational videos like this and others. We've done training events. We've got a great Facebook community that I highly suggest you join if you're an operator and want to ask interesting questions about, why is my lagoon pink, or how do I get more nitrate removal in my lagoon? And if you go to lagoons.com/LDIB and you sign up for these different components that we do have Lagoons Do It Better hats that we send around for people that join the club. And one last slide, we have another one of these webinars coming up shortly. It is Wednesday, December 14th. Ben Scheckman's he's a great presenter. He's giving a presentation on industrial lagoon aeration. So if you're an industrial customer out there, check this out. And finally, we're on to Q&A. Just about 5 minutes over, and I am ready. So we look at the list here. Will the presentation slide deck be available? Yes, that can be done. This will also be presented. This will be saved on the university. You can watch this anytime. Another question along those lines. So another person made a great comment that some engineers design in phases rather than designing for the worst case scenario. So if they don't know what the 20-year scenario is going to look like, but they have expectations, they cut it in half, they design a 10-year scenario and then a phase 2 to meet that 20-year scenario. That is another option as well. Another member asked about phosphorus removal. That's a different conversation, obviously, than energy efficiency, but we recommend flocking it out with some kind of coagulant or flocculant, settling it out in the lagoon system, or depending on your limit, removing it with some kind of device, whether it's a sand filter, a disc filter. In general, mechanical removal is the best way to go. BioP is very difficult to get reliably for low limits from a phosphorus removal standpoint. Is it true that turbo blowers are not very good for temperature swings as well as summer and winter operation in Canada? So that's going to be very dependent on the turbo blower. I know some manufacturers have temperature conditioning devices to kind of temper the temperature coming into the blower. And I also know that turbo blowers generally are a bit more fickle. Not only some manufacturers of turbo blowers can you put them outside. So I think winter and summer operation has a big impact on where you put it. Do I put it outside or do I put it in a building? I can't speak specifically to temperature swings. I have not seen that issue. We have some turbo blowers installed in North Minnesota, and I know you're talking about Canada, but Minnesota is about as Canada as we get in the United States from a people and temperature standpoint. And those blowers weren't running great. They're super happy about it. I have not seen any issue. They're placed in a building. They're piping exterior air into the building, and they actually liked it so much they bought another one. So I'm not seeing that as an issue, but I suggest you talk to your blower manufacturer about that one. Last question that has come in here, looking for a discussion on blowers versus compressors, especially with the use of fine bubble aeration lines. My experience, and we used to use compressors, way back when the company started, we used to do very low airflow, and compressors were a good fit because they're relatively inexpensive for producing 4 or 5 SCFM. My experience with compressors, though, is that they're great at pressure and they're great at being small and inexpensive, but they're not good at volume of flow. And blowers are great at pressure and flow. The jump up from a compressor to a blower is going to be a huge cost typically, but in general, for 99% of lagoon systems that we see for fine bubble aeration, blowers are the way to go. Unless, if you're looking at a backyard pond that's not wastewater and you just need a couple of SCFM out there, a compressor is a good way to do it. Compressors can get significantly higher pressure, but it's rare that we see lagoon systems that are deeper than 20 feet, which might be a 10, 12 PSI system. Blowers can do 12 PSI all day long. If you're getting up towards 30, 40, 50 PSI, I don't know where you're pumping air, but compressor might be better suited for that application. So I'm going to wrap that up here. I appreciate the questions. My email is at the bottom here, as is my phone number, and I am happy to talk about this stuff and take a look at your email questions. If I can't answer it, I might be able to pass it along to somebody that does. We in general appreciate you coming to these. We've had a really, really great attendance. You'll get a survey at the end of this. Let us know how we did. Please respond to it. If you think that Brady talks too long and went 6 minutes over and talks too fast, let us know. If you think we're doing a great job, let us know. What we want to do is do it better for you guys and provide more useful content. So your feedback is essential. I appreciate you guys coming around. Thank you for your time, and I will talk to you later.